Hello and welcome to Fluid Mechanics. My name is Dr. Mark Taylor, lecturer in Civil Engineering. So this is Unit 4, and we're going to look at the fundamentals of flow. So this is the fourth unit in the module, and we're going to look at discharge, continuity, energy, and momentum. So during this lesson, I aim to explain the representation of fluid flow, define streamlines, street lines, and path lines, introduce the concept of a stream tube, explain the difference between laminar and turbulent flow, and look at the experiments that Reynolds undertook. I'm going to provide explanation of how actual fluids behave due to viscosity, and I'm going to introduce the concept of frictional and minor losses in pipes and some of the appropriate calculations. So at the end of this lesson, which also includes the tutorial questions, you should be able to understand the basic types of flow, understand some of the theoretical and experimental approaches to measuring flow, describe the difference between laminar and turbulent flow, explain the concept of a Reynolds number, understand and use the continuity equation, and be able to calculate frictional losses in pipelines. Fluid statics is a study of fluids at rest or relative equilibrium, and it's relatively straightforward. Fluid dynamics is a bit more complex, and it's beyond the scope of this lecture and this module. However, several approaches can be used to analyse or predict fluid flow. Experimentation, the importance of which cannot be overestimated, theoretical analysis, made possible with simplifying instructions. Theoretical analysis must also be validated and verified experimentally. And if we derive a form of theoretical solution and use experimentation to determine appropriate empirical coefficients. So when we talk about real fluids, these are quite difficult to analyse theoretically. Often what we do is approximate to an ideal fluid. And in the case of an ideal fluid, for example, we neglect viscosity. And there's lots of useful results that can be obtained from this approximation. So all fluids are compressible in some respects. However, since we're dealing with liquids, we will assume that compressibility effects may be neglected, and thus assume that the flow is incompressible. In general, all fluid occurs in three dimensions, so that velocity, pressure, and other factors vary with reference to three orthogonal axes. In some problems, the major changes occur in two directions, or even only in one direction. Changes along the other axis, or axes, in such cases can be ignored without introducing major errors, and this then simplifies the analysis. Flow is described as one-dimensional if parameters such as velocity, pressure, and elevation, describing the flow at a given instant, vary only along the direction of flow and not across the cross-section at any point. Conditions in a body of fluid can vary from point to point, and at any given point can vary from one moment of time to the next. Flow is described as uniform if the velocity at a given instant is the same in magnitude and direction at every point in the fluid. If at the given instant the velocity changes from point to point, the flow is described as non-uniform. In practice, when a fluid flows past a solid boundary, there will be variations of velocity in the region close to the boundary. However, if the size and shape of the cross-section of the stream of fluid are constant, the flow is considered to be uniform. A steady flow is one in which the velocity, pressure, and cross-section of the stream may vary from point to point, but do not change with time. If at a given point conditions do change with time, the flow is described as unsteady. In practice, there will always be slight variations of velocity and pressure, but if the average values are constant, the flow is considered to be steady. So here are four possible types of flow. So the first two are steady flow, the first one being steady uniform flow, so conditions do not change with position or time. For example, the flow of liquid through a pipe of uniform bore running completely full at a constant velocity would be an example of this type of flow. Steady non-uniform flow, the conditions change from point to point, but not with time. So the velocity and cross-sectional area of the stream may vary from cross-section to cross-section, but for each cross-section they will not vary with time. For example, the flow of a liquid at a constant rate through a tapering pipe running completely full. Now we'll look at unsteady flow. So unsteady uniform flow, at a given instant of time, the velocity at every point is the same, but this velocity will change with time. For example, accelerating flow of a liquid through a pipe of uniform bore running full, such as would occur when a pump is started up. The last one is unsteady non-uniform flow. So the cross-sectional area and velocity vary from point to point, and also with time. For example, think about a wave travelling along a channel. So there are two main alternatives to studying the behaviour of fluids. We can study a specific element of the fluid, or we could define the system to be studied as a fixed region in space, known as a control volume. So flow is described as one-dimensional if the factors or parameters such as velocity, pressure and elevation describing the flow at a given instant vary only along the direction of flow, not across the cross-section at any point. In two-dimensional flow, it is assumed that the flow parameters may vary in the direction of flow and in one direction at right angles, so that the streamlines are curves lying in a plane and are identical in all planes parallel to this plane. Thus, the flow over a weir of constant cross-section is shown below, and infinite width perpendicular to the plane of the diagram can be treated as two-dimensional. A real weir has a limited width, but it can be treated as two-dimensional over its whole width, and then an end correction can be introduced to modify the result to allow for the effect of the disturbance produced by the end walls. So let's now have a look at the Reynolds number and what that means. So in 1883, Osborne Reynolds built apparatus to discharge water from a tank into a glass tube with an outlet controlled by a valve. A very simple experiment, but fundamentally important to the subject of fluid mechanics. The rate of flow could be controlled by the valve. A fine filament of dye from a separate reservoir could be injected into the entrance of the tube. So Osborne Reynolds' observations showed that two entirely different forms of fluid flow existed. This was demonstrated by him in 1883 through his experiment. The rate of flow was controlled by a valve at the outlet and a fine filament of dye injected at the entrance to the tube. At low velocities, it was found that the dye filament remained intact throughout the length of the tube, showing that the particles of water moved in parallel lines. This type of flow is known as laminar, viscous, or streamline, the particles of fluid moving in an orderly manner and retaining the same relative positions in successive cross-sections. As the velocity in the tube was increased by opening up the outlet valve, a point was eventually reached at which the dye filament at first began to oscillate and then broke up so that the colour was diffused over the whole cross-section, showing that the particles of fluid no longer moved in an orderly manner, but occupied different relative positions in successive cross-sections. This type of flow is known as turbulent and is characterised by continuous small fluctuations in the magnitude and direction of the velocity of the fluid particles, which are accompanied by corresponding small fluctuations in pressure. So you can see some sketches showing laminar and turbulent flow. Top left, this is laminar flow, and you can see that the dye filament remains intact as we move through the pipe. In turbulent flow, we can see that the dye filament breaks up as we move along the pipe. The image below shows a chimney. On the left, a chimney on a calm day, where the smoke rises vertically, but on a windy day, you can see we have what looks more like turbulent flow. So the Reynolds number is the most famous dimensionless number in fluid mechanics. It is the criterion to distinguish between laminar and turbulent flow. It's a ratio of the inertia force on an element of fluid to the viscous force on that element. The parameter which determines whether the flow is viscous or turbulent is this Reynolds number, and you can calculate it as shown. Typical values for the Reynolds number in excess of 4,000 would be turbulent flow, between 2,000 and 4,000 would be intermittent zones of laminar and turbulent flow, and less than 2,000 would show that you had laminar flow. So let's now look at the subject of friction. So frictional losses are a loss of pressure or head that occurs in a pipe or duct flow due to the effect of the fluid viscosity. The term refers to the power lost in overcoming the friction between two moving surfaces. The characteristic of frictional loss is that it is proportional to the pipe length. Frictional loss per unit weight of flowing fluid in a pipe is denoted by H subscript F. The flow in a pipe network may be required to pass through a variety of fittings, elbows, or abrupt changes in area. Additional head losses are encountered, and primarily as a result of flow separation. The energy eventually is dissipated by violent mixing in the separated zones. Therefore, these losses will be minor losses, which are denoted by H subscript R. So for the entire pipe system, the total head loss should be the summation of the frictional losses and the minor losses. So there are two factors which affect the magnitude of flow resistance: the cross-sectional area and the wetted perimeter. The hydraulic diameter, or the hydraulic radius, is often used to reflect the influence upon flow resistance with the two factors above. The hydraulic diameter for circular, square and rectangular ducts are shown. A minor loss can be expressed as a product of the flow velocity head and the coefficient. The minor loss coefficient, in this case zeta, varies with different local devices. So we can see a sudden contraction, a gradual expansion or contraction, and a slow radius bend are examples. The table shown shows the minor loss coefficients for a sudden contraction of the pipe diameter concerning the ratio of A2 to A1. The table shown provides examples of minor loss coefficients for sharp inlets, inclined inlets, gates, cyclone separators, and check valves. So the complex effect of the actual installation situation is unknown, but what we can do at this stage is we can calculate the total head with the pressure or energy loss. You need to sum up all the frictional losses and minor losses together, and this forms an aggregation of head loss. Considering the aggregation of head loss, the total head loss of a pipe can be expressed as shown. To help undertake the calculations, we can transfer the minor loss factors into an equivalent length, and this is known as the equivalent length of minor loss. So the total head loss can be simplified then to the calculations shown, where L is the total drag length of the pipe. So now we're going to have a look at the Darcy-Weisbach equation. So in 1850, the work of Darcy and Weisbach and others deduced a formula for pipe frictional loss. The equation is shown here, where lambda is a dimensionless coefficient called the friction factor. And we'll look at how to use this equation in the tutorials in more detail. So based upon experimental data, the relationship between lambda, the Reynolds number, and the change in the diameter were plotted by Lewis Moody in 1944. The chart became known as the Moody chart for pipe friction, and it can be used for circular, non-circular and open channel flow. If the Reynolds number and relative roughness are known, then it can be used to find the value of the Darcy-Weisbach friction factor. The calculation of losses in turbulent flow is dependent on the use of empirical results, and the most common reference source is the Moody chart as shown here. It's a logarithmic plot of lambda versus the Reynolds number for a range of relative pipe roughnesses, K over D, or in this case epsilon over D. This type of data presentation is commonly referred to as a Stanton diagram. A typical Moody chart is shown here. I've also made a short video demonstrating how you can use a Moody chart for designing pipe systems. So now I'm going to introduce the concept of streamlines and how we visualize flow. So fluid flow, in this case air, can be represented by streamlines, street lines and path lines. Such lines can be visualized by smoke particles, liquid or solid particles mixed into the fluid stream, making the flow patterns visible to the naked eye. Flow visualization makes an invisible flow pattern visible. So a useful visual picture of a pattern of steady fluid motion is obtained using streamlines. These are lines either imaginary or traced out by successive fluid particles throughout the flow stream. The tangent to a streamline indicates the direction of the velocity vector at a particular point. When drawing or creating with smoke streamlines, it's important to only include a few so as to make the patterns clear. There should be no crossing of the streamlines occurring because the velocity vector and the direction of the streamline coincide with each other. Since there is no flow across a streamline, one streamline always stays coincided with a free surface or a solid boundary. And when streamlines around a body are observed, they vary according to the relative relationship between the observer and the body. So these imaginary lines are tangential to the velocity of the fluid particles. Streamlines have the same flow direction as the particles of liquid. The fluid particles cannot flow across the streamlines. Flow direction of the streamlines is the same as the direction of the velocity. Streamlines cannot cross since that would imply that the fluid has two different velocities. They are difficult to analyse, but in steady flow they are identical to streak lines. In steady flow, the injection of a dye can be used to visualise them. So a streamline when drawn is tangential to the velocity vector at every point in the flow at a given instant, where u, v and w are the velocity components in the x, y and z directions. A region bound by streamlines is called a stream tube. There's no flow across the streamlines, as a fluid inside a stream tube cannot escape across its walls, hence the stream tube behaves like an imaginary pipe. Hidden in the definition of streamline is the fact that there cannot be a flow across it, i.e. there is no flow normal to it. Sometimes we pull out a bundle of streamlines from inside a general flow for analysis. Such a bundle is called a stream tube, and it's very useful for analysing flows. So, in summary, a path line is the line traced by a given particle, and this is generated by injecting a dye into the fluid and following its path by photography or other means. A streak line concentrates on fluid particles that have gone through a fixed station or point. At some instant of time, the position of all these particles are marked and the line is drawn through them. Such a line is called a streak line. A timeline is generated by drawing a line through adjacent particles in flow at any instant of time. In two-dimensional flow, the stream tubes will be defined by the streamlines. The black lines are shown below. It's assumed here that the fluid flow above the centre of the card is two-dimensional. The stream tube is indicated by the shaded grey region, and all the fluid entering it must remain within it. So now we're going to introduce the subject of continuity. So the total quantity of fluid flowing in a unit of time past any particular cross-section of a stream is called the discharge, or flow at that section. It's measured in terms of the mass rate of flow, or the volume rate of flow. The mean velocity can be calculated by dividing the volume rate of discharge by the area of the cross-section. So with the exception being nuclear processes, matter is neither created nor destroyed. The principle of conservation of mass can be applied to a fluid, considering any fixed region in the flow constituting a control volume. So the mass of fluid entering per unit time must equal the mass of fluid leaving per unit time plus an increase of mass of fluid in the control volume per unit time. So let's consider the stream tube shown. We know that fluid can't cross the walls of the stream tube, so the mass entering station number 1 equals the mass leaving at station number 2. So the mass flow rate at station number 1 must equal the mass flow rate at station number 2. So we could write out this general continuity equation for steady flow in a stream tube. For incompressible steady flow, for which the mass density is constant, the general equation of continuity can be simplified further. And this is the general equation of continuity for steady incompressible flow, and can be used with a high degree of accuracy for steady flows in liquids. So in summary, we touched on the subject of real and ideal fluids. We considered uniform and steady flow. We introduced the concept of Reynolds number, and we looked at his research. We contemplated the differences between laminar and turbulent flow. I briefly introduced the Darcy-Weisbach equation. I also looked at Moody charts, and then we considered streamlines, street lines and tubes. We also now know how to apply the conservation of mass to a fluid, and we know the general equation of continuity for steady incompressible flow. So along with the tutorial questions for Unit 4, next week we're going to look at one-dimensional flow. We're going to look in more detail at the conservation of energy and momentum. So thanks for listening, and bye for now.